Hi everybody, this is Dr. Bricker here with some hints for homework number 9. Now homework number 9 is over several different chapters. It's over chapter 8, which is balancing forces and torques. And then we jump up to chapter 14, simple harmonic motion. The part of that chapter we're going to do is mass on a spring. And then we do a little bit also with standing waves. So this homework assignment's a little bit longer, that's why I'm giving you a few extra days to do it. So let's get started. The first one here is from chapter 8. A 68 kilogram student stands on a very light, rigid board, as you can see in the picture. Okay, the rigid board that rests on a bathroom scale at each end. So there is the left side and the right side. And part A is what is the scale reading on the left scale? What is the scale reading on the right hand side? Okay, so 68 kilograms, we can figure out the weight. That would be 68 kilograms times 9.8. The weight is the mass times gravity. So you can figure out the weight. We just don't know how it's distributed. How much is on the left scale, how much is on the right scale. So it's not going to be the same because the person's not standing in the middle. Well, so let's take a look at this. Okay, so this is basically the picture. Normal left, normal right, and the weight of the person's pulling down. There's a normal force on the board from the person equal to the weight. So I've just, instead of writing normal from the person on the board, I just called it weight, which is m times g. And we're trying to figure out the normal force on the left and the normal force on the right. So part A is to figure out the normal force on the left. One thing that you know, regardless of how we do this, normal left plus normal right is equal to the weight. So whatever's up is equal to whatever's down. The problem is I can't solve for normal left here because I don't know what normal right is. I've got one equation with two unknowns. I can't solve that uniquely. I could use torques though to try to figure this out. And with torques you're free to pick whatever pivot point you want. So the torques are balanced about whatever pivot point you want. So I'm going to pick this as my pivot point. And let me balance the torques about that point. So I have the weight. The distance from the pivot point to the weight is 0.5 meters. So that's the torque because of the weight. That's going to have to be equal to the torque from normal left. So the weight is making it rotate counterclockwise. Normal left is making it rotate clockwise. But it's not going anywhere, so those are balanced. So I've got normal left, and then the distance from the pivot point over to normal left is 2 meters. And then I can solve for normal left, because that's the only thing that I don't know. All right, I've got the weight here. I've got that distance. Normal left I don't know. That's 2 meters. So the weight times 0.5 meters divided by 2 meters is normal left. So it turns out that the weight divided by 4 is equal to normal left. So 0.5 over 2. Okay, so when you get the weight, m times g, this is how much normal left is. And then if you want to, you can come back over here and figure out normal right. Normal right is weight minus normal left. And then you could figure out normal right that way. Another way of getting normal right is to pick this as the pivot point. So if I pick this as the pivot point, I could balance the torques about that point. So let me quickly do that here, just to give you an idea. The way I described is perfectly good. Get normal left this way. Normal right is the weight minus normal left. Or I could pick the red as the pivot point, and then I would have the torque because of the weight equal to the torque because of normal right. And then I could do weight, distance from the pivot point to the weight, 1.5 meters, is equal to normal right, and then the distance to the pivot point, 2 meters. And then you see that the weight times 1.5 over 2 is equal to normal right, or 3/4 of the weight. Okay, and that's how it's distributed. 1/4 of the weight is on the left scale, 3/4 of the weight is on the right scale. Okay, let's look at the next one. Okay, another balancing force and torques problem. You're carrying a 4-meter long, 21 kilogram pole to a construction site. When you decide to stop for a rest, you place one end of the pole on a fence post and hold the other end 35 centimeters from the tip, or 0.35 meters. And again, here's the video tutor solution. You could take a look at this and get some hints from another source of how to solve this problem. We want to figure out how much force must you exert to keep the pole motionless. So you're resting one end on a fence post, you're carrying part of the load on your shoulder. How much of that load are you carrying? So it's not going to be half or anything like that, because you're not right at the same exact point. You're 0.35 meters from the tip. So let's draw this out. With so many of these torque and force problems, you really have to have a nice picture. So let's take a look at it. Okay, so here's what I have for the picture. Here's the pole. It's a uniform shape, so I know the center of gravity of the pole is right in the middle. So that's that special point where you can consider all the mass to be located. So that's the weight of the actual pole. And again, it's right in the middle because it's a uniform shape. Now I've rested one end on a fence post. So here's a fence post. So I'm calling this normal from the fence post. Weight is pulling straight down. And then here's my shoulder, 0.35 meters from the end. So the goal is to figure out what is the force that I'm exerting on the pole here. So you can't just do this with forces. The reason is you don't have enough information. Normal from shoulder plus normal from fence. Those are both up. That's equal to the weight, which is down. And you can't solve for it, though, because you don't know normal fence. You do know the weight, but you don't know normal fence, so you can't get normal shoulder. Luckily, we could use torques. So I'm trying to figure out normal from the shoulder. So if I pick this as the pivot point, then there's no torque at that point because it's at the pivot point. Normal fence doesn't exert a torque at the actual point of rotation. So if I pick this as the point of rotation, then I don't need to know that force because it's not providing a torque. So the torque from the weight about this pivot point would make it rotate counterclockwise. That has to be equal to the torque from the shoulder, which would make it go clockwise. Okay, so remember what torque is: force times, whatever lever arm you have here. So you have the weight, and then the distance to the pivot point. That's 2 meters. That's got to be equal to normal from shoulder, making it go the other direction, and then this distance. Looks like 2 meters, and if this is 0.35, that's 1.65, so that total distance is 3.65 meters. And then you can do a little bit of algebra, solve for normal shoulder. And then if you wanted to, they don't ask for it, you could go back and get normal fence from this equation. Sort of similar to the last problem, actually. All right, let's look at the next one. Okay, still in Chapter 8 here. A vendor hangs an 8-kilogram sign in the front of his shop with a cable held away from the building by a lightweight pole. Okay, so here's a pole, cable. Okay, excellent. The pole is free to pivot about the end where it touches the wall. So there's some kind of a hinge there. Okay. Okay, so let's read it one more time. Vendor hangs an 8-kilogram sign. Okay, so the sign over here is 8 kilograms. Okay, here's a cable and a lightweight pole. So we're assuming that this pole on its own doesn't have any mass. So the pole on its own, although it does in reality have some mass, we're assuming it's really, really small. The weight of the pole would make it rotate clockwise, but we're assuming it's massless. And we want to know what is the tension in the cable. Okay, so let's set up a picture for this one. Okay, so we've got the weight out here, we've got tension this direction. There's actually forces here at the pivot point. There's got to be some kind of normal force from the wall this way. There's probably also a hinge force either up or down. We can't really tell right now which direction that is. So the forces here at the pivot point, we definitely have a normal force this way. Maybe there's another part of a hinge force that's vertical, either up or down. We're not sure what that is yet. The thing is, if we pick this as our pivot point, which it's actually kind of a natural pivot point because that's where it would rotate from, then we don't need to know the forces at this pivot point. So this tension, we could break into its components. This is T in the Y direction, T in the X direction. Those have to be equal to each other, or They have to have components. What has to be equal to each other is the torques. So there's a torque from Ty that would make it go counterclockwise. There's a torque from the weight about that pivot point that would make us go clockwise. Those torques have to be equal to each other. It turns out this problem actually simplifies a lot now that I'm looking at it, and you'll see why in just a minute. This is 60 degrees, so this has to be 30 degrees. This is 60, that sort of thing. So the torque, because of the weight, has to be equal to the torque because of tension in the y direction. Okay, so torque from the weight would be the weight, and then the distance to the pivot point, which is just called L, we don't know what it is, that's got to be equal to the torque because of the tension in the y direction. So that would be the force, and then the distance to the pivot point. So it simplifies a lot because this actually cancels out. There's an L and an L that cancels out. So it turns out in this problem, the weight is equal to the tension in the y direction. So in terms of hinge forces here, there actually is not a vertical or a horizontal one. There's just the normal force this way. I know there has to be a normal force to the right because I got a Tx to the left, and all the forces have to be balanced. So the normal force here at the wall has to be equal to the tension in the x direction. Okay, so the weight is Ty. That doesn't actually completely solve the problem. You can get what Ty is, right? This is just m times g is Ty. That's this component. You have to do a little bit of trig to figure out the overall tension, though. So once you figure out the overall tension, if you wanted to, knowing this angle in Ty, you could get Tx, and then you know that has to be equal to the normal force. Okay, all right, let's look at the next one. Okay, so if you hold your arm outstretched with your palm up, like the picture, the force to keep your arm from falling comes from your deltoid muscle. As you can see here, here's the deltoid muscle. Assume that the arm has a mass of 4 kilograms, and the distances and angles are shown. So here's the center of gravity of the arm. 0.38 meters from the pivot point. The deltoid muscle is connected here. And we want to know what force must the deltoid muscle exert, so the force by the deltoid muscle, and by what factor does this force exceed the weight of the arm. So this shows you the mechanical disadvantage of where the deltoid muscle is attached. So just kind of like the lab that you're doing with the human arm model, this is similar to that. The human arm model, we looked at the bicep muscle. Here we're looking at the deltoid muscle. All right, again, picture is essential to solve these problems. So let's make a nice picture. Okay, so here's what I have. Center of gravity of the weight, 0.38 meters from the pivot point. Here's the deltoid muscle, so maybe I'll just call this force from muscle. It's 0.17 from the pivot point over to this muscle, and it's acting at an angle of 15 degrees. So the arm's not going anywhere. So the weight would make it rotate this way. This force from the deltoid muscle would make it rotate counterclockwise, but it's not going anywhere, so those torques are equal to each other. So the torque from the weight is equal to the torque from the bicep muscle. Now the torque from the weight is the force, and then the distance to the pivot point, 0.38 meters. It was 38 centimeters. I put it into meters. This has to be equal to the perpendicular part of the bicep muscle. So force muscle perpendicular. Right, that's the part that actually would make it rotate counterclockwise. So force muscle perpendicular, and then times 0.17 meters. So you have to break this into components, figure out how much of this force is perpendicular. And then it's not too bad to solve it. Let me give a better picture of that little blow up of this area here. So this is theta, which is 15 degrees. You want to figure out how much of that force is this way. From my picture, this is what I had. Force, muscle, perpendicular. Right, this is the part of the muscle force that does not make it rotate. That's the parallel part. This part of the force does not make it rotate. This part does. So you'll have to figure out, right over here to clean up the picture a little, you have to figure out this in terms of that, based on the angle. So hint. So sine of theta. So sine of theta, opposite side, divided by this. So solve for this muscle force perpendicular in terms of this force, and then plug it back in there. However you want to do it. You could actually right now figure out force muscle perpendicular, and then take that in conjunction with this formula and figure out how much the muscle force actually is. They're not asking for the perpendicular part, they're asking for the overall part. But to use torques, you need to know the perpendicular part, and then work backwards and get the actual muscle force. All right, let's look at the next one. Okay, so for Chapter 8, which is the balancing forces and torques, I didn't do anything with elasticity. I'm just looking at the balancing force and torques part of that chapter, and you'll see that when you look at the notes. So after Chapter 8, we're going up to Chapter 14, which is simple harmonic motion, and we're just doing the first part of that chapter, which deals with masses on springs. We are not looking at pendulum motion. It's cool stuff, we just are not going to have enough time to cover everything. So no pendulum motion, just masses on springs. I believe it's the first 4 sections of that chapter. But I'll put that in the notes so you know exactly. Okay, so onto this problem. When a guitar string plays an A note, the string vibrates at 440 hertz. So that's the frequency. So what is the period of vibration? So this still works with Chapter 6, the circular motion chapter. We know that the period is 1 over the frequency. So if this is the frequency, the period is 1 over the frequency. So if you take 1 divided by 440, you'll get the period. And you can review that section here. Okay, so without putting anything on paper, that's the way to do that problem. Next problem. An air track glider attached to a spring oscillates between the 10 centimeter mark and the 57 centimeter mark on a track. The glider completes 15 oscillations in 37 seconds. We want to know what is the period of oscillation, what's the frequency, what's the amplitude, what's the maximum speed. Okay, first couple of questions aren't too bad. Let's put it on paper though. Okay, so here's what we have. We're going between 10 centimeters and 57 centimeters. So it's something like a mass on a spring. Here's a mass. It's going all the way up to 10, going back to 57, going to 10, going to 57. So it's actually, while you have the picture here, to figure out the amplitude, the total distance we're going is 47 centimeters. So there's an equilibrium position. So this would be something like it's attached to a spring. And you pulled it over here to 57, you let it go, the spring is going to push it this way, and then go back that way. Trying to think if that's the best way of describing it. Yeah, that's pretty good. Take it here, let it go, it's going to shoot this way. Here's the equilibrium position where the spring is relaxed, and then it's going to have enough momentum to make it here, stop for an instant there, come flying back this direction, and so on, and keep going back and forth, back and forth. So the amplitude is the distance from the equilibrium position to one end or the other end. So if this total distance is 47, the amplitude's got to be half that. So the amplitude, that's what big A is, would be 47 centimeters divided by 2. So 23.5 centimeters. I can't remember if we want it in centimeters or meters, but make that adjustment. Okay, as far as the period goes, it's the amount of time for one oscillation. So 37 seconds divided by 15 oscillations. That'll give you the amount of time for just one oscillation. What about the frequency? Well, it's 1 over the period. So once you get part A, the frequency is 1 over the period. Okay, the last part, the maximum speed. So when you read through the chapter, the maximum velocity, 2 pi f times a. So once you do the second part and the third part, it's not too bad to get the maximum velocity. The maximum velocity actually occurs right here. So you let it go here, it speeds up, speeds up, speeds up. As soon as it passes here, the spring force is back this direction, and then it starts slowing down. But that's where the maximum speed occurs. Okay, good. Let's look at the next one. Okay, the motion of a nightingale's wingtips can be modeled as simple harmonic motion. Okay, excellent. In one study, the tips of birds' wings were found to move up and down with an amplitude of 9 centimeters or 0.09 meters and a period of 0.9 seconds. What is the wingtip's maximum speed? So that's just like we did in the last part of the previous problem. 2 pi f times a. So 2 pi times the frequency. Well, here's the period. You can get the frequency from that. And then the amplitude is given in the problem, 9 centimeters, so 0.09 meters. So 2 pi times the frequency times the amplitude. The maximum acceleration, so again, if you ever forget these formulas, just hit the review part here. And this will take you to the section in the book, and we can look up the formula for the maximum acceleration. There's a lot less intuition in this stuff, like simple harmonic motion. You can't just think of these formulas off the top of your head. So you've got to build a nice little formula sheet, at least to keep everything straight. Okay, let's go down here. Here's the formula for position versus time. So the maximum position would be equal to just the amplitude. The maximum velocity, same thing up here. Whoops. When this argument is 1, that gives us the maximum velocity. And let's see if we can put it all together down here. Okay. There'll be a formula coming up in just a second. Maximum velocity, 2 pi f times a. So read through that section. What about the maximum acceleration? It's this formula. 2 pi f, that whole thing squared, times the amplitude. So that would give you 4 pi squared f squared times the amplitude. That's the maximum acceleration. Excuse me. The author does a really good job in this section about talking about where all these things come from. So make sure you take a look through this chapter and look at the video that he has talked about here at the beginning of the chapter. Okay? Very good, especially the part with masses on springs. All right, let's look at the next one. Okay, so we've got a 505 gram mass oscillates with an amplitude 13 centimeters on a spring. Here's the spring constant. Determine the period, determine the maximum speed, determine the total energy. Okay, so let's write all this stuff down and then use some of our new simple harmonic motion tools. Okay, so we know it's a mass on a spring. Simple harmonic motion. Here's a big takeaway for simple harmonic motion. If we can identify it as simple harmonic motion, this is the relationship between period, mass, and spring constant. That's what this is, the spring constant. If you notice, the period, the amplitude doesn't come in anywhere here. If you take a mass on a spring and give it a really big amplitude, it's going to have the same period if it has a small amplitude. If you think about it, if you stretch a spring out a lot and let it go, it's going to be moving really fast. If you don't stretch it as much, it's not going to be moving as fast. But on the other hand, not stretching it very much, it has a small distance to cover, and it turns out that the period's the same. So same period whether you stretch a spring a lot and let it go or a little bit, because the amplitude doesn't come into play at all in this formula. So great. If you want to get the period, they actually give you the mass. They give you the spring constant. you can figure out the period. Here's the formula right there for the first part. That's the great thing about knowing it's simple harmonic motion. It's very complicated motion, actually. If you take a mass on a spring, compress it, let it go, the mass goes this way, comes back, maximum speed in the middle. The acceleration is not constant. It's very, very complex, actually. But if it's simple harmonic motion, this is the formula for the period. To get the maximum speed, just like we did before, 2 pi f times the amplitude. They give you the amplitude. You'll get the period from the first part, then you can get the frequency because the frequency is 1 over the period. And then if you want to get the total energy, the total mechanical energy would be 1/2 mv max squared. That's when all of the energy is kinetic energy. That's when it goes through the equilibrium position. Or you could use this if you want to, 1/2 k a squared. This is when all the energy is spring potential. This is when all of the energy is kinetic. So this occurs when x is equal to 0. This one occurs when x is equal to plus or minus. Whoops, let me scoot that up a little bit. This one occurs when x is equal to 0. All the energy is kinetic energy. This happens at the turning points, when we are at plus or minus a. That's when all of the energy is spring potential. In between a and 0 and minus a, we have a combination of kinetic and spring potential. But at these specific points, this is what we know. So either use this or this to get the total energy. Do it both ways. It should come out to be the same for you. All right, let's look at the next one. Okay, so from Chapter 14, we just did the first 4 sections of Chapter 14, Simple Harmonic Motion, Mass on a Spring. We're just doing the first 2 sections of Chapter 15 to get enough background information to be able to do standing waves from Chapter 16. Again, I will give you more detailed information about what we're covering, but I just thought I'd let you know now, give you a little heads up. Okay, so Chapter 15, the wave speed on a string under tension is 200 meters per second. So you take a string, maybe you attach one end to the wall, you hold the other end, you pull it tight, and you flick the string, and a pulse is going to go down the string. And in this problem, the wave speed, the speed of the wave moving down the string is 200 meters per second. What is the speed if the tension is doubled? All right, let's take a look at this. Okay, so here's what we have for tension and a characteristic of the string and the speed of the pulse. So if you make the tension greater, the speed's going to be greater. It's not directly proportional. We have a square root here, but it also depends on the thickness and the linear mass density, really, of the string. So a thicker string compared to a thinner string, the thicker string, the pulse is going to move slower. So this is called mu, the mass per length. So the speed, it depends on the tension. I did F of t because I don't want to confuse it with period, which also comes up in some of these problems. And then the mass per length, it's just a characteristic of the string. So mass per length we have here. So we're going to double the tension. What happens to the speed? Well, doubling the tension doesn't double the speed because we have this square root relationship. So the speed is proportional to the square root of the tension. So what I can do is write it like this. You know, new tension is to old tension as this new speed is to old speed as this new tension is to the old tension. So I can do that. I can set up a proportion as I've shown you before. So the mass per length is the same for each of them. So that doesn't come into play, right? Those are the same. It's the same string. Okay, so this new speed, v prime, is the old speed times this ratio, new tension to old tension. But they're telling you that the new tension is twice the old tension. So you've got to take the old tension, multiply it by 2 to give you the new tension. So I can plug that in here too. And then the force of tension actually cancels out. And we're left with V times the square root of 2. So doubling the tension doesn't double the speed, it increases it by a factor of the square root of 2. Okay? Very good. All right, let's look at the next one. Okay, so here's the next one from chapter 15. A scientist measures the speed of sound in a monoatomic gas to be 449 meters per second at 20 degrees Celsius. What is the molar mass of the gas, and what element does it consist of? So there's a temperature dependence and a dependence on what the actual gas is made out of to determine the speed. So in chapter 15 we have transverse waves. Like waves on a string would be a transverse wave. So as the disturbance moves up and down, like you flick the string up and down, the wave moves perpendicular to that. That's a transverse wave. An example of a longitudinal wave where the disturbance is in the same direction as the propagation of the wave. That's a longitudinal wave, and a sound wave would be that. Like the cone on a speaker moves in and out, and the sound moves, in the same direction as that. So although we're mostly focusing on waves on strings, I did include one problem dealing with this longitudinal sort of wave. So what is the molar mass of the gas? And then what does this consist of? So this is actually a way of determining what your sample is made out of. Send sound through there, figure out how fast it's moving, know the temperature, work backwards, figure out what the sample is actually made out of. So let's take a look at this. Okay, this is given the speed, temperature in Celsius. We need it to be in Kelvin, so add 273 to the Celsius temperature to give you the Kelvin temperature. This probably to a lot of you has the flavor of doing some chemistry, which it really does to me as well. It's a monoatomic gas, so gamma in the formula for a monoatomic gas is 1.67. This is the gas constant. You are probably familiar with that from chemistry as well. 8.31 joules per mole. And we're trying to figure out how many grams per mole. So you have everything here except for what you're looking for, the molar mass. So you have to do a little bit of algebra, square both sides, speed squared, gamma RT over the molar mass, the grams per mole. So then the molar mass turns out to be gamma RT over V squared. Now be careful with the units. They want the answer, whoops, scoot it up here so you can see it. That's gamma RT V squared. Monoatomic gas, gamma 1.67. So be careful when you get the answer. You want it in grams per mole. This won't come out in grams per mole, right? This is going to be in SI units. Okay, so get the number for that, and then once you figure out how many grams per mole, look at the periodic table and see what you're dealing with, right? You'll get a number for grams per mole, then you have to kind of decode that. Whatever grams per mole you get, what is it actually made out of then? So look it up in a periodic table, which is actually given to you on mastering. Let me show. Okay, so when you click periodic table here, you'll have to go and see which one of these corresponds to how many grams per mole you just got. Okay, very good. And again, don't forget you can always hit review immediately and go through and read this section. I already have it set up here for us. Here's describing the formula. This is kind of the physics way of looking at the formula with Boltzmann's constant. This is the chemistry way of looking at it with the gas constant. And big M here is the molar mass, the amount of grams. Well, it'll come out in kilograms per mole, but you'll have to turn it into grams per mole. And then a little description of what gamma is, things like that. So that's always at your fingertips, literally. All right, let's look at the next one then. Okay. So we just did the first two sections of chapter 15 just to get a little introduction about waves. And then chapter 16, there's a lot of good things in chapter 16, but the part that we're going to focus on are standing waves. So like waves on a string, waves on a guitar string, that sort of thing. Okay, so that's the first few sections of chapter 15. Again, I'll give you more detailed information, but I believe it's the first 4 sections of this chapter as well. Okay, so let's jump into this problem. A 2.2 meter long string, so that's the total length of the string here. 2.2 meters long, fixed at both ends, tightened. We get a wave speed of 40 meters per second what is the frequency of the standing wave shown? Okay, so let's take a look at this. Okay, so we've got the standing wave on a string. So the tension is exactly right for the sort of string we have, and we actually can set up a standing wave that looks like this. And we want to figure out the frequency of this. The first thing to know is what kind of wave, what mode do we have here? So if you count the amount of high spots, these are called the nodes. 1, 2, 3, 4, 5, 6. So this is 6, mode 6. It's just the amount of high spots. Okay. The reason that we need to know that, and again, this is the mode, not the mass. So be careful. This is the mode. 6 high spots. We could use that to figure out the wavelength. So the wavelength that we have here is 2L over the mode, which is 6. So we've got 2 times 2.2 divided by 6. So this will give you the wavelength that we have displayed on the wave up here. So be careful. That's a big common mistake. This M means mode, not mass. It's the amount of high spots. So why do I need this? Well, if I get the wavelength and I know the speed, which is given in the problem, I can figure out the wavelength, and then the speed is the frequency times the wavelength. So if you take the speed divided by the wavelength, that will give you the frequency. I guess the way to think about this, if you had a wave, why is the speed the frequency times the wavelength? Really, another way of looking at it, it's the wavelength divided by the period. So if you had a wave, something like this, this is the wavelength. That's the distance between the peaks. And how long does it take to go from peak to peak? Well, that's the period. So if this peak were traveling over to here, it travels the distance of one wavelength. Whoops, let's write a T up here. It travels a distance of a wavelength. How long does it take to go from here to here? Well, that's also the period. And that turns out you could write it like this, then the frequency times the wavelength. So really it's the wavelength divided by the period to give you the speed. But I also know that the 1 over the period is the frequency. That's where this equation really comes from here. Okay, let me recap. So from the picture, I know the mode is 6 by counting the high spots. The wavelength, the formula for the wavelength is 2L divided by the mode. So you'll get a number for this. The wavelength is measured in meters, a certain amount of meters. And then once you have the wavelength and the speed, you can calculate the frequency. Okay, let's look at the next one. Okay, we've got a bass guitar string, 89 centimeters long, fundamental frequency of 30 hertz. What is the wave speed on the string? So what we did in the previous chapter, where the speed was the tension divided by previous chapter, the speed was the square root of the tension divided by the mass per length. It still works in this chapter. We won't really need it for this problem, but just keep that in mind, that everything that we did from chapter 15 still works here. Okay, let's draw this one out. Okay, so fundamental frequency means mode is 1. That's just a way of saying it's the first mode. This is what it actually looks like. This is usually what you hear. So the length of the string is 0.89 meters. Fundamental frequency is 30 hertz. What is the speed? Well, the wave speed is the frequency times the wavelength. Luckily, they give me the frequency. Now, it's tempting to say, well, the wavelength is just this length. It's not. The wavelength is 2L over M. 2L over M. So it's actually 2 times 0.89 divided by 1. Good, so 1.78, I guess. It's been a while since I've done math in my head. I think that's okay. So that's the wavelength. This is really half of a wavelength, right? I mean, it's not a complete wavelength. When you pick M is equal to 2 here, now that actually looks like a wavelength, right? It turns out it is. For this one, when M is equal to 2, the wavelength is 2L over 2, right? Because this is mode 2. So the only time that the wavelength is actually equal to the length is when you're in mode 2. Okay, so going back to this, you're given the frequency, you have to calculate the wavelength, and then you can put it in here. All right, excellent. Let's look at the next one. Okay, here's another one. A guitar string, linear mass density, 2 grams per meter, stretched between supports that are 60 centimeters apart. The string is observed to form a standing wave with 3 antinodes. So, good, 3 antinodes, or that means 3 high spots, when driven at 420 hertz. What is the frequency of the 5th harmonic? And then part B, what is the tension in the string? Okay, let's sketch this out. Okay, so the antinodes are the high spots. This is an antinode. The nodes are the low spots. There's always at least 2 nodes. 1, 2, and then there's other low ones as well. 1, 2, 3, 4. There's 4 nodes. There's always 1 less antinode. So antinodes. So they're telling you that the 3rd harmonic is 420 hertz. And we want to figure out the 5th harmonic. Well, you know, all the different harmonics are just multiples of the fundamental frequency. So for example, this 3rd harmonic means it's 3 times the fundamental frequency. So you can figure out the fundamental frequency. It's just 1/3 of this 3rd harmonic. So 420 divided by 3, 140. That's the fundamental frequency. So if you want to figure out the 5th harmonic, this is 5 times the fundamental frequency. So that looks like 5 times 140 would be 700 hertz. Okay, and then you want to figure out the speed. So this is the first part. And then you want to figure out the wave speed. So the wave speed is the frequency times the wavelength. So for example, if you use the 5th harmonic frequency, you've got to use whatever that wavelength corresponds to. Or you could say this is the 3rd harmonic times whatever the corresponding wavelength is. So you'll have to figure out either, I mean, you have the 5th harmonic here. You could figure out this wavelength, 2L over, I'll do it like this. This wavelength would be 2L over 5, or you could do the 3rd one, which would be 2L over 3, right? Because the wavelength is 2L over M. So the wavelength corresponding to the 5th harmonic would be 2L divided by 5. That's what I have here. The wavelength corresponding to the 3rd harmonic would be 2L over 3. And then to get the speed, you know, use whatever one you want here. Okay, let's look at the next one, though. That doesn't quite finish up this problem. That gives you the wave speed. And we really want to figure out the tension. So the speed is the tension divided by the mass per length. So if you square both sides, you get speed squared, which you'll still need to get the speed, is the tension divided by the mass per length. So the speed squared times the mass per length will give you the tension. So there's a little bit more work to get the tension. Just be careful. The mass per length has to be in kilograms per meter, right? And I think they give it to you in grams per meter. So this would be 2 to the minus 3rd kilograms per meter. Okay, now we can go on to the next problem. Okay, so the lowest note on a grand piano has a frequency of 27.5 hertz. So that's the fundamental frequency. The entire string is 2 meters long and has a mass of 400 grams. Okay, so for this one, you're going to have to actually calculate the mass per length of the string. So this would be 0.4 kilograms divided by 2 meters. That would give you the mass per length. And then the lowest note given in the problem, okay, good, that's the fundamental frequency. The vibrating section is 1.9 meters long. So you're given 2 different lengths. This one goes along with 400 grams, so you could use that information to figure out the mass per length. And the vibrating section is actually 1.9 meters long. And then we want to know what tension do you have to have this correct frequency of 27.5. So on a grand piano, you set the tension of the string, and then you get a certain frequency. Like on a guitar string, there's tuning pegs. You turn those, you increase the tension or decrease the tension. In doing so, you change the frequency. So when you see people tuning a guitar, they're adjusting it to get the correct tension. All right, let's take a look at this one. Okay, so again, you use this information to get the mass per length, whereas in the last problem they just gave it to you. The frequency is given, the wavelength that corresponds to that frequency from the formula 2L over M, and L is the part that's actually vibrating. So 1.9 meters times 2, so it looks like this turns out to be 3.8 meters. The reason I can do that is then I can get the speed. Right, it's the frequency times the wavelength. You can get the wave speed, and we're trying to figure out the tension. So a few steps. First you got to get the wave speed, and then the speed is the tension divided by the mass per length. So there's a little bit more involved in this problem in the sense that you have to calculate the mass per length. It's just not given to you. So same idea, square both sides here. Tension divided by mass per length. Same idea though. The speed squared times the mass per length will give you the tension. So be careful. I'm calling it force of tension. Mastering Physics is calling it T for tension. It's the same thing. It's just confusing if we have got too many T's floating around. Is it tension or is it period? That's why I'm calling it force of tension. All right, if you have any questions, let me know. I'll talk to you soon. Bye-bye.